残酷な天使のように少年よ神話になれ青い風が今胸のドアを叩いても私だけをただ見つめて微笑んでるあなたそっと触れるもの求めることに夢中で運命さえまだ知らない痛いけな瞳だけどいつか気づくでしょうその背中には未来目指すための羽があること残酷な天使の手で窓辺からやがて飛び立つほとばしる熱いパトスで思い出を裏切るならこの空を抱いて輝く少年よ神話になれ
Oh, hello. Let's get started. Okay, so we're going to start today off with some more L'Hôpitals. We're going to talk a little bit more about some of the other cases, the more interesting things that L'Hôpitals can do for us. But first, we got into it a little bit yesterday, but let's take a step back. Let's think about the way that the 0 over 0 indeterminate form really lets us deal with infinity over infinity or negative infinity over negative infinity over positive infinity, or infinity over negative infinity indeterminate forms. This guy gives you all of these. So, how? The basic way to think about it is that if the limit as x goes to a of f of x is the same as the limit as x goes to a of g of x, and both of those guys are, say, plus or minus infinity, then the limit as x goes to a of 1 over f of x is the same as the limit as x goes to a of 1 over g of x, and both of those guys are 0. So, noticing that f of x over g of x is the same as, just think about it for a second, 1 over g of x over 1 over f of x. Just think about, dividing by 2 is the same as multiplying by 1/2, right? Dividing by 1 over f of x is the same as multiplying by f of x. So, since this is true, having infinity over infinity, I should just put plus or minuses there, I guess, is really the same as 0 over 0 in terms of indeterminate forms. So the gist of this is basically just that if I have the limit as x goes to a of f or g, or both of them, plus or minus infinity, then I can turn that into a limit that goes to 0 instead, just by turning things into reciprocals. So since dealing with f over g is no different than dealing with 1 over g divided by 1 over f, I can turn the indeterminate form infinity over infinity, that's this one, into 0 over 0. That's this one right there. So basically, all we're doing is we're taking a different indeterminate form and we're recasting it as the 0 over 0 indeterminate form. We're taking all of these guys here and we're recasting them as the 0 over 0 indeterminate form. That's why we can deal with infinity over infinity, negative infinity over negative infinity, and on and on and on. This is why we're able to handle it. So, cool. This is the basic sort of motivation for all of the rest of the tricks we're going to do with L'Hopital's rule. We're going to figure out all of the different ways we can turn something, some ill-behaved, not a number type thing, into a nice indeterminate form, into the 0 over 0 indeterminate form. We won't so much focus on doing these tricks every time we actually do a problem, but it is the justification, at least theoretically, for why we're able to do L'Hopital's rule to so many different things. All right, let's see the first case. Okay, back into another example, just to illustrate the general idea of what we're going to do here. So the first thing we're going to encounter, the first type of extended L'Hopital's rule outside of that infinity over infinity case, which was pretty easy to manipulate into a 0 over 0 indeterminate form, we're going to look at the indeterminate form of something like 0 times infinity. This is for functions of the form f times g, taking the limit as x goes to a for f times g, where the limit as x goes to a of f of x is 0, and the limit as x goes to a of g of x is either plus or minus infinity. Okay, these guys would naturally produce if I could break up the limit across the product. You know, if this was well behaved, I totally could. Could I just take this limit and break it up across that product? If it was well behaved, I could. But stuff like 0 times infinity, it's not necessarily clear what this should be. What should it be? Should it be 0? Should it be infinity? Really unclear. So we can't directly apply L'Hopital's rule to limits of this form. And it's generally pretty risky to jump to conclusions about this type of limit. However, let's run through an example illustrating how we can recast this limit in one of the indeterminate forms we already know how to deal with. So, first thing we're going to do, we're going to look at an example and get some intuition. All right, let's evaluate the limit as x goes to infinity of x squared times sine of 1 over 4x squared. So, if we just look and see what's going on, the limit as x goes to infinity of x squared is, well, put a really big number and square it. What do you get? A very big number. This doesn't exist, but the way it doesn't exist is by going off towards infinity. So the limit as x goes to infinity of x squared is infinity, as we like to say. Okay, what about the limit as x goes to infinity of sine of 1 over 4x squared? So, since sine is a continuous function, we can pull this limit inside. Sine of the limit as x goes to infinity of 1 over 4x squared, and the limit as x goes to infinity of 1 over 4x squared. 1 over 4 times a very large number squared is quite close to 0, so we'll end up with sine of 0, and as we all know, that's just 0. So this is exactly this 0 times infinity indeterminate form. This has the form 0 times infinity or infinity times 0. Doesn't matter what order you multiply anything in. You know, it's multiplication, you can do it either way. At least for real numbers. Cool. Or extended reals, whatever you want. So there's a very commonly employed technique that converts this form of a limit into either a 0 over 0 or infinity over infinity indeterminate form. It's very straightforward. It's pretty much what we just talked about. It's dividing by the reciprocal. So let's rewrite the limit really quick. So x squared times sine of 1 over 4x squared is the same as sine of 1 over 4x squared divided by 1 over x squared. That is, if you divide by 1/2, you're multiplying by 2. Yeah? Same sort of thing going on here. So now notice that the limit of the top guy, we already computed that. That's this thing up here. That's what's going on there. And down here, if I take a limit as x goes to infinity of 1 over x squared, well, 1 over a very large number squared is quite close to 0, so this goes to 0. And once again, we're back in that 0 over 0 indeterminate form. The limit of the top goes to 0, limit of the bottom goes to 0. We're in the form we started with. We're able to apply L'Hopital's rule. So we had to manipulate it so it's in this form to start with. Once we're here, now we can apply L'Hopital's rule. It's not the case that just because you can manipulate it into L'Hopital's rule, you can immediately just start deriving willy-nilly and get the right answer. You gotta put it in the right form before you start taking any derivatives. So now that we got it in the right form, let's take a derivative of the top function. So sine of 1 over 4x squared, a classic chain rule situation. Derive that outside function, sine. We'll get cosine. Leave the inside function, 1 over 4x squared alone. You're good. All right. 1 over 4x squared is just 1/4 times x to the negative 2. So if we take a derivative of the inside function now, we'll get 1/4 times minus 2x to the minus 3. Okay, cool. We derived the top function. Now if we derive that bottom function, 1 over x squared, which you could rewrite as x to the minus 2, we'll just get minus 2x to the minus 3 by the power rule. And that's exactly what we have right here. So this equals sign, this is by L'Hopital's rule. That's where we're applying it. Okay, so we've applied this. Now I'm going to take this 1/4, I'm going to throw it outside the limit, just like this. And then I'm taking the limit as x goes to infinity of cosine of 1 over 4x squared, because without that 1/4, cancel, cancel. Cancel each other out. So we already computed basically the same thing for sine, but now we're just doing it with cosine. So we can draw that limit inside that cosine function, because cosine is continuous everywhere on the entire real line. And then we'll see that we get cosine of 0. That is, the step that's in here is just going, oh, okay. This thing is equal to 1/4 of cosine of the limit as x goes to infinity of 1 over 4x squared. And that guy is just equal to 1/4 of cosine of 0. And that's just 1/4, because cosine of 0 is 1. So this is how we get that final answer, 1/4. Cool, okay. So there was a little bit of pre-processing we had to do. We had to put the function in the right form, that is, in a form so we had a 0 over 0 indeterminate form. And then we applied L'Hopital's rule, got to our final answer just using the stuff we did in the last video. All right, cool. Let's go further. Okay, similarly to what we just did, we can also use L'Hopital's rule to deal with limits of the form the limit as x goes to a of the quantity f of x minus g of x, where the limit as x goes to a of f of x is infinity, and the limit as x goes to a of g of x is infinity. These kinds of limits are generally denoted by something like infinity minus infinity, this type of indeterminate form. And L'Hopital's rule cannot be directly applied to something like this because L'Hopital's rule is for 0 over 0 indeterminate forms. We can adapt a version of L'Hopital's rule for this the same way we did for the infinity over infinity case and the 0 times infinity case. So we'll get a new one for the infinity minus infinity case. All of these ambiguous, not numbers, these are not real numbers by any means. These are, all in quotation marks, infinity over infinity, 0 times infinity, not really numbers. We're not really ever going to get these as answers. These are just types of ways that we can fail to get an answer using any traditional tools. So, L'Hopital's rule once again to the rescue, and we're going to figure out a way to recast infinity minus infinity indeterminate forms in terms of 0 over 0 or infinity over infinity indeterminate forms. Now, since we can always recast a infinity over infinity indeterminate form as a 0 over 0 indeterminate form, really, we're totally good. So everything always boils down to this guy, 0 over 0. Cool. Let's try out an example. So, example 24, let's evaluate the limit as x goes to infinity of the quantity x minus the square root of x squared minus 3x. All right, this limit has the form infinity minus infinity. Why? Well, just double check real quick. The limit as x goes to infinity of x is, well, what does x get close to as x gets close to infinity? Infinity. And of course, the limit as x goes to infinity of the square root of x squared minus 3x. Well, since square root is continuous, at least for positive values of x, that's definitely true. We can pull it on inside. We get the square root of the limit as x goes to infinity of x squared minus 3x. And just running on through that, limit as x goes to infinity of x squared minus 3x is going to be infinity. Take a big number and square it. That minus 3x, chump change, doesn't even matter. So we'll get square root of infinity. Take a big number and take the square root of it. It's still pretty big, right? So there you go. You get out infinity there as well. So this guy, infinity, this guy, infinity, in the limit. So infinity minus infinity. This is not what we want. This is not a good answer. What we need to do is we need to take this infinity minus infinity indeterminate form and recast it in a form to which L'Hopital's rule can be applied. So, first thing we're going to do is we're going to factor an x from the expression and form a quotient. This is basically the gist of how you always deal with these guys. L'Hopital's rules always about quotients. We need a product that we can convert into a quotient. So, we're going to pull an x out of both terms. First term already got an x in it. This term, it's got some x's, but we need to do a little bit more to pull an x all the way out. So, gist of it is that we'll pull an x squared out of both of the x squared and the minus 3x terms. This will give us x squared times the quantity 1 minus 3 over x. And that's all still inside that square root. Just doing some basic algebraic manipulations. Cool. Okay, now since the square root of a times b is the square root of a times the square root of b, I can take this x squared right here and pull it out and turn it into an x. So once I get rid of that guy, it just turns into an x right there. Okay, turning it into an x, now notice I have an x and I have an x. So I can pull that x on out, pull it right outside the function, or outside of those square brackets, and I'll get the limit as x goes to infinity of x times the quantity 1 minus the square root of 1 minus 3 over x. So here, now I've got x times something. All right. Notice, as I take the limit of each of these guys as x goes to infinity, this guy right here, that'll go towards infinity as x goes towards infinity, obviously. And 1 minus the square root of 1 minus 3 over x, this will go to 0, because 1 minus 3 over x goes to 1 as x goes to infinity. And then we just end up with 1 minus 1. Okay, so infinity times 0, we're using the exact same trick as last time. All we're going to do is we're going to take multiplication by x and turn it into division by 1 over x. So now this top guy, this will go to 0, just like we said, as x goes to infinity. And this bottom guy, 1 over x, this will also go to 0 as x goes to infinity. Cool. This new limit has the form we want in 0 over 0. Perfect. We can apply L'Hopital's rule. One way to proceed is to do a change of variables. This might make our lives a little tiny bit easier. And also, it's a pretty good illustration of the fact that if I just relabel things, nothing really changes. All I have to do is keep track of the way that relabeling things changed my problem. So let's talk about applying a change of variables. Basically, I'm going to take 1 over x and I'm just going to name it t. It's like when we write y equals f of x. Basically, I'm just, instead of writing a y, I'm putting a t. I'm just going to replace a complicated thing with a simple thing. Now the thing to keep track of here is that as x goes to infinity, t, which is 1 over x, goes to 0. Because if t is 1 over x, putting in bigger and bigger values makes t closer and closer to 0. Yeah? So, and it's important here, it's not just going to 0. It's going to 0 from one side. That is, as x goes to infinity, we're not talking about the two-sided limit. It's not going to 0 from values below 0. You're never going to get a negative, at least, when you're plugging in big positive values of x. So really, we can take this limit as x goes to infinity and turn it to a limit as t goes to 0 from values greater than 0. That is, coming in from the right-hand side to 0. So if you got a little number line, there's 0. We're coming in from this direction as opposed to this direction. We're just doing this one. Okay. And that's because when we're putting in big positive values of x, we're getting out small positive numbers, but only positive numbers. And that's why we're only approaching from this direction. So we take this limit, we turn it into that bad boy right there. And now this guy becomes a t, and 3 over x, well, 3 over x is just 3 times 1 over x, and so that's 3t. All right, so that's t down here, and this guy is 3t. Okay, now we got a new form of our expression. We converted one limit into another, and we took this expression and substituting things in, we got the limit as t goes to 0 from the right of 1 minus the square root of 1 minus 3t over t. Cool. We're still in a L'Hopital's form. Notice that. As t goes to 0, the top still goes to the exact same thing. Changing our labels should not change the values of a limit. If somehow by changing our labels, we've changed the values of a limit, we've done things wrong. We've somehow not considered some extra complication that's going on there. But for simple substitutions like this bad boy, you don't even have to worry about it. It should just always be the case. That's a good sanity check to make sure that you substituted correctly. Make sure the limit comes out the same under your new labeling. All right, cool. So we got a L'Hopital's form right here, and this guy going to be a whole lot easier to derive. So we derive the bottom function t, d dt of t is just 1, and the top function 1 minus the square root of 1 minus 3t, well, this is just 1 minus the quantity 1 minus 3t to the 1/2. And if I take a derivative just using the good old-fashioned chain rule, and let's actually do that out in full detail just so nobody gets a little bit lost on that. Give ourselves a bit more room. All right. So taking d dt of square root of 1 minus 3t, all we have to do is notice that this is just taking a derivative of 1 minus 3t to the 1/2, which we can handle very straightforwardly just using a chain rule. Okay? And I'm going to not line up my equals entirely, just so I have enough room here. This guy is just equal to, well, bring that 1/2 down. 1/2, 1 minus 3t to the 1/2 minus 1, that's negative 1/2, times the derivative of 1 minus 3t. That's just minus 3. And so this turns into minus 3 all over 2 square root of 1 minus t. And hey, wouldn't you know it, this is exactly what I have right here. The only difference is that minus is gone because I had a minus right here. Cool. All right. Now, when I take this limit, it's not even bad. The limit as t goes to 0 from the right of the top is just 3. And the limit as t goes to 0 from the right of the bottom is, well, 2 times the square root of the limit as t goes to 0 from the right of 1 minus 3t, which is just 2 times the square root of 1. Okay, that's just 2. So, bam! Got our answer, 3 over 2. Very cool. So we started out with this limit right here, and doing some relatively judicious manipulation, we got ourselves an answer even though this thing was in the indeterminate form infinity minus infinity. We just manipulated it into the indeterminate form 0 over 0 and applied the classic, the amazing, the super useful L'Hopital's rule, however you want to say it. All right, another case down. Let's see if there's any more we can do. Okay, we're back to another indeterminate form, and this one's probably the trickiest. People have a lot of trouble dealing with this one in general, but really it's not too bad. It's pretty much the same type of thing as when we dealt with functions like x to the x. These are the indeterminate forms, 1 to the infinity, 0 to the 0, and infinity to the 0. All of these are a number to a power, or not a number to a power, something to a power. And because of this, they all come from limits of the form, the limit as x goes to a of f of x to the g of x. And we can, of course, replace x goes to a with x goes to a plus or minus, or x goes to plus or minus infinity. That is, if it works for the two-sided limit, we can definitely make it work for either of the one-sided limits, and we can also make it work as we just go off in either direction. Cool. But, like before, L'Hopital's rule cannot be directly applied to these indeterminate forms. We have to express them in the 0 over 0 indeterminate form, or if you want, infinity over infinity. But really, infinity over infinity, as we talked about at the very beginning, gives you the 0 over 0 indeterminate form. And so really, it's always still about this 0 over 0 indeterminate. Here's the gist of how we can deal with this. So if you'll recall, e to the natural log of x is just a fancy way of writing x. That is, e to the x and ln of x are inverse functions. Now you do have to take a little bit of care making sure that your values of x are in the right place. You can't plug in negative numbers to natural log and get out anything sensible, at least in terms of real numbers. So there is that minor caveat, but generally we'll be able to gloss over it. There's no need to focus on it right here. Okay, so next up, what we're going to do with this is we're just going to notice that if this is true, then e to the natural log of f of x is the same as f of x. That is, just plug in f of x for x. Just plug in f of x in either spot in x appeared. Should still be true, right? We're just relabeling x with f of x. All right, good stuff. So, taking this guy, we can notice that f of x to the g of x is the same as e to the natural log of f of x to the g of x. And since since a to the b to the c is just a to the bc, we can just bring this g of x on in and multiply. That is, this is just e to the g of x times the natural log of f of x. And we could write this as the natural log of f of x times g of x. I'm just putting that g in front so we don't get confused and accidentally think that it's inside that natural log. Just for convenience, order of multiplication doesn't matter at all for real valued functions. Cool. So we turned this guy into this guy. This is something we can deal with. Why? Well, let's go into it. Let's make sure we really get it. So, to get one of these indeterminate forms up here, one of these guys, from a limit like this, what we need is that f is going to say 1 and g is going to infinity, f is going to 0 and g is going to 0, or f's going to infinity and g is going to 0. Something like that, right? Just looking at what we have right here, that's what we need. Okay. Any one of these cases, using the fact that we can recast it like this, we can turn into a 0 over 0 indeterminate form. Basically, the procedure we're going to do is as follows. Since the limit as x goes to a of f of x to the g of x is exactly the same by this little argument right here, giving us that these two things are the same. This is exactly the same as the limit as x goes to a of e to the g of x times the natural log of f of x. We can just use the fact that this is a composition. E to the g of x times the natural log of f of x is a composition. It's g of x times ln f of x plugged into e to the x. So, since e to the x is continuous, I can take this limit inside the function. That is, I can turn this limit right here into e to the limit as x goes to a of g of x times the natural log of f of x. And then, if I can do manipulations on this part right here, let me get a different color, if I can do manipulations on this guy and get a value, if this is, say, equal to L, then my answer at the end of the day will be e to the L. Just evaluate this limit up top, this guy here, and then we'll have e, we'll have some number, and we'll get e to the L. All right, cool. Evaluating this guy here is the part that will occasionally be tricky. So, let's talk about a procedure and let's try an example. Okay, here's the general way we're going to deal with this kind of thing. This is important enough, we'll call it a theorem. You know, it's at least a complicated enough procedure that it warrants its own name. So, Theorem 15, how to deal with the indeterminate forms 1 to the infinity, 0 to the 0, and infinity to the 0. And really, infinity to the 0 plus or minus infinity to the 0 doesn't even matter. Okay, cool. So, if we have a limit like the limit as x goes to a of f of x to the g of x, and we get the indeterminate form 1 to the infinity, 0 to the 0, or plus or minus infinity to the 0, when we try to naively evaluate it, this is not the value of the limit, just to really force that. These are not the value of the limits. These are just the way that we would fail to find the value if we naively tried to evaluate the limit. So, if we get one of these ones when we try to do it just straight away, here's what we'll do to handle it. Here's what we'll do to get the actual answer. We'll analyze the limit, let's just call it L, the limit as x goes to a of g of x times the natural log of f of x. This limit, I promise you, can be put into the form 0 over 0 or infinity over infinity. We can handle both of these guys. This guy will give us this type of indeterminate form. This is something we can deal with using L'Hopital's rule. This is what we talked about with the first couple of examples. All right. Now, when you get a finite value of L out, then just like we went through, the limit as x goes to a of f of x to the g of x, the limit we started with, right up there, is just e to the L, whatever that finite value we got out from this limit right here. If L is infinity or negative infinity, then the limit as x goes to a of f of x to the g of x is either infinity or it's equal to 0, respectively. That is, if L is infinity, then you'll get e to the infinity, basically. That is, e to a really big number is still a really big number, and so you get out infinity as your answer. The limit fails to exist, but that's how. If you get negative infinity instead of infinity, then you're going to get 0, because e to the negative infinity, if you want to think about it like this is not technically correct, but e to the negative infinity, you can think about that as being 0. Basically, e to the negative, big number, let's just put a big number n, is just 1 over e to the n. And if e to the n is quite large, 1 over e to the n is very close to 0 when n is large. That's where we're getting this part from. Okay, so this negative infinity case, basically we're just using this logic right here to conclude that we'd get out 0. Okay, cool. So these are all the situations that can happen. We're really applying L'Hopital's rule twice here, but it's just kind of hidden in the technicalities because no one wants to go through that long justification we just started with. All you got to do is analyze this limit. You don't even honestly have to remember how you get there, though you probably should. It's not a bad idea. And if you get out a finite number, the answer to this limit is e to the L. If you get infinity or negative infinity, then you get out, respectively, either infinity or 0. Bam. Easy recipe. Let's try following it. Okay, here we are back with a super classic example, x to the x. Let's evaluate the limit as x goes to 0 from values bigger than 0, so from the right-hand side of x to the x. All right, pretty easy to see that the limit as x goes to 0 of x to the x is just 0 to the 0, right? So we've got this indeterminate form. We're going to use our two-step procedure we just talked about. Basically, we're just noticing along the lines of that long justification we gave that x to the x is just e to the x times the natural log of x. We use this all the time when we were dealing with chain rule for the first time. This was a classic example that we used a lot. So, very familiar, just the silly e to the natural log of x equals x trick. So we take this guy, and we're going to start, just like we said in that last little theorem, by evaluating this limit, the limit of the top part. The limit as x goes to 0 from the right of x times the natural log of x. This limit has the form 0 times infinity. Let's check it out. So as we're going to 0 from the right, you're getting x going to 0, and natural log of x, really it's going towards a negative infinity if we want to be very, very careful here, but who cares? It can get absorbed in the 0, and 0 times infinity, same thing. So it's still not a number, either way. 0 times negative infinity, 0 times infinity, same business, doesn't even matter. It's just not a number. But we can use the same tricks we've just talked about to put this in the form infinity over infinity, so we can apply, once again to the rescue, L'Hopital's rule. We could also take this and put this in the form 0 over 0 if we felt like it, but we don't have to. We can leave it like this. It'll be a little easier. So the idea is we take the limit as x goes to 0 from the right of x natural log of x, and we notice that multiplying by x is the same as dividing by the reciprocal, dividing by 1 over x. So now, as we go to 0, notice the top is still going to negative infinity, and the bottom is now going to infinity. So we're back in this case over here, that infinity over infinity case. or negative infinity over infinity. Either way, it's not a number, but it's an indeterminate form that L'Hopital's rule can handle. So we just take a derivative on the top and a derivative on the bottom. Derivative of natural log, this is a L'Hopital's application right here. Derivative of natural log is just 1 over x, and the derivative of 1 over x, which is just exactly the same as x to the minus 1, using the power rule, is minus 1 over x squared. That is, this is minus x to the minus 2, just the power rule, yeah? So, notice, minus 1 over x squared is the same as minus 1 over x times 1 over x. Do you agree with this? Yeah. Okay, so if I have 1 over x over 1 over, or minus 1 over x squared, that's the same as having 1 over x over minus 1 over x times 1 over x. These two guys cancel. So we get out 1 over minus 1 over x, and that's kind of ugly, so let's just turn that into minus x. That is flipping and getting rid of the fraction there. We'll just get out this minus x. This equal sign right here, this is just algebra, as is this guy right here. So 2 algebraic steps, 1 L'Hopital step, and then 1 evaluation of a limit. So what does minus x get close to as x gets close to 0? It gets close to 0. That plus barely even matters here, not really at all. Whether you're going from the left or the right, minus x gets close to 0 as x gets close to 0. So bada boom, we get 0. But wait, this is not our answer. This is this part. We just found the limit of that L value right there. We found the limit as x goes to 0 from the right of x natural log of x. That's only, switch to a different color just to highlight it, that's only this chunk right here, not the whole thing. So when we want to get our answer, we just take what we had and we exponentiate it. That is, the limit as x goes to 0 from the right of x to the x is just e to the L, where L is this value we just found, which is 0. So e to the L, e to the 0, anything to the 0, other than 0 or infinity or something like that, is 1. Bada boom. We got our final answer. It's 1. So it seems a little bit complicated, but really all you have to do is you have to know this little intermediate step, and you have to remember to exponentiate it to get your answer. Kind of inconvenient, but ultimately pretty convenient that we can even deal with them in the first place. Cool. As I've gotten deeper and deeper into the rich, fulfilling world of fingerboarding and fingerboarding culture, videos like this have stopped just being cool or amazing. They're much more than that. Seeing something like this is a spiritual experience for me now. It moves me in a very deep and emotional way. This is different. This isn't like the time I tried to convince that bouncer that I too was a bouncer for more than 4 hours. I love watching fingerboarding and thinking about fingerboarding. And fingerboarding is a very big part of who I am, okay? So stop getting mad at me when I bring it up when we're talking. If you want to be a part of my life, you're gonna have to accept that fingerboarding will be part of your life, okay?
めでたいな。おめでとさん。